Hello, in this video we study how to change variables in double integrals. Let's remind you about the chain rule in calculus 1. The chain rule says if you have function f and g, x, right? And you want to find the derivative of this function, so you evaluate the function f prime at gx and then multiply with the derivative of the inside function. For integrals, we have integration by substitution. That is the inverse of the chain rule, right? So suppose that you have integral from a to b, f of x dx, and the function x depends on u, right? And from here you have dx equal to g prime u du. By doing so, you can rewrite your integral as cd f of gu, g prime u, and du, where cd are new integration limits. Make sense? So that is integration by substitution. That's what we learned in calculus 1. But now, if you have function of 2 or 3 variables, how can we change that? Suppose that you have some double integral over some region R, right? F of x and y dA. And your function x depends on new variables u and v, x, u, and v. Y also a function of u and v, right? And you want to change the variables. In the previous video, we studied polar coordinates, cylindrical coordinates, spherical coordinates. And, if we go from rectangular to cylindrical coordinate, you need to add r. Remember that? And if you go from rectangular to spherical, you need to add rho square psi of phi. Why do we have such functions added to the integral when you go from one to another coordinates? That is the main purpose of today's lecture. Let's talk about Jacobian of function x and y with respect to u and v. Suppose that you have two functions x and y, and the Jacobian of x and y with respect to the u and v is defined as determinant of partial derivatives. In the first row, you have partial derivative of x with respect to the u and v. And in the second row, you have partial derivative of y with respect to the u and v. Okay? Your function may be depending on many variables. Make sense? So if you have more than x and y like z, or more than 3 variables, that's fine. You still can define the Jacobian, right? And if x and y depends on more than 2 variables, no problem. You still can do Jacobian. Anyway, in the first row, you collect all partial derivatives of x. Or actually, what is this? This is gradient of x, right? You see that? That is gradient. So rows of Jacobians are gradients of functions right here. Make sense? And the second row is nothing but the gradient of y. Okay? So we will use Jacobian to change variables in double and triple integrals. But before that, we need to practice a little bit. Let's find the Jacobian of the following. X equal to r cosine of theta and y equal to r sine of theta. Alright? So this is the standard polar coordinates, right? So if you have x and y, you are in rectangular coordinate, you go to r and theta, you are in polar coordinate. I just mentioned previously, we need to add r, right? When you change integrals. All right, so how to see that? You need to find Jacobian of this. That is determinant. In the first row, you have gradient of x. So you consider dx with respect to dr, dx with respect to d theta. In the second row, you have gradient of y, right? dr and then dy d theta. You differentiate this function with respect to the r, you get cosine of theta. You differentiate that function with respect to the theta, you get negative r sine theta, right? And in here you move to the y. Derivative with respect to r is sine theta, and the derivative with respect to theta is r cosine of theta. Now you calculate the determinant of this. That is nothing but, product of this, subtract product of this. So you get r cosine square theta plus r sine square theta. So when you take r out, you get r cosine square theta plus sine square theta. That is nothing but r, because cosine square plus sine square is just 1. You see, that's how we get r. Makes sense? In general, if you want to change variables in your integral, you need to find the Jacobian, and in the integral with the new variables, you have to multiply with the absolute value of the Jacobian. Okay, this is true for triple integrals too. Make sense? When you go from rectangular to polar coordinates, you have the following one: as f of r cosine of theta, that is x, right? F of r sine of theta, that is y, times Jacobian is r. You see that? d r d theta. That's why we get this. Make sense? Now let's consider triple integrals. Suppose that you have the following triple integral over some q f x y z dv, and you want to rewrite this in cylindrical coordinate, and we know the following formula: q prime f r cosine x cosine theta r sine theta z, and times r, right? dz dr d theta. That's what we used in the previous video, right? So we still have r right here, but now we have function of 3 variables. So how to see that? Again, I apply the same formula right here, right? For triple integral, but I need to find Jacobian. Makes sense? Because now we have 3 functions. So the first function is x equal to r cosine of theta. The second function is y equal to r sine of theta. And the last function is z equal to z. All right, now let's find Jacobian. So the Jacobian will be determinant of 3 by 3 matrix, right? The first one, I differentiate x with respect to the r, I get cosine of phi. Then with respect to theta, I get negative r sine of theta. But when I differentiate x with respect to the z, I get 0, right? Similarly, I have sine theta in here, r cosine theta, and 0. That is gradient of y, this is gradient of f of x, right? And the last row is gradient of z. So z with respect to r is 0, with respect to theta is 0, and with respect to z is just 1. And once you calculate determinant of this guy, that is nothing but determinant of cosine theta minus r sine theta r cosine theta, and this is exactly equal to to r. That's why you have r right here. Okay, so let's go for spherical coordinates. We need to verify the following formula: q f x y and z dv equal to triple integral over q prime f of r psi phi cosine theta r psi phi psi theta, and finally, no, we have rho right here. Sorry, we have rho right here. We have rho right here. Okay, and the last one is rho cosine of phi. So remember that we multiply with rho square sine of phi, right? When you go from rectangular to spherical, d rho, d phi, and d theta. How to see this? Okay, again, we need to calculate Jacobian. Okay, so for that, I have three functions in here. First one is x, second one is y, the last one is z, right? So I will not copy, I just write Jacobian right away. I can find gradient of x. I differentiate with respect to rho, I get psi phi cosine theta, right? And then the next one, I differentiate with respect to phi. I get rho cosine phi and cosine theta. And when I differentiate the function with respect to theta, I get negative rho psi phi psi of theta. Okay, that is the first row of the Jacobian. The second row, psi phi psi theta rho cosine phi psi theta, and rho rho psi phi cosine theta. All right, now let's move to the gradient of z. I have cosine phi, negative rho psi phi, and 0 right here. So basically, you need to find the determinant of this 3 by 3 matrix. Please, I would like to challenge you to find this determinant, and you find exactly this is equal to rho square psi phi. If you have solution, please send that to me. Now, let's move to examples. The first example is we have some region bounded by lines x minus 2 equal to 0. Right here, x minus 2y equal to negative 4. That is right here. X plus y equal to 4. This is this straight line, and x plus y equal to 1. Okay, this region is not, not that beautiful. Okay, and we know that, if you integrate over this region and you want to rewrite in terms of arithmetic integrals, remember that? So like if you fix x, right? You fix x, you need to make some vertical line, and you consider, intersection of that straight line with the lines in here in order to find the interval of y. Makes sense? But in that situation, you need to consider several cases. Like this case, or from here, you have considered this case, or you move to this case, and you move to this case. Because, for each intervals in here, the intersections may be very different. Because we have 4 straight lines in here. Makes sense? So, that is not a good idea. If you consider your integral in the order dx dy, this is almost the same. So you need to find horizontal, right? That means you fix y, and then you have to consider different case like this. Makes sense? So not good. We need to do something else, right? Here's the thing. They ask us to find a transformation T from S to R. This is your S, this is your R, and they fix R for us. They say, yes, what is R? They use new variable U equal to 1, U equal to 4. You see, we already have rectangular, right? And here we have -4, 0 right here. Makes sense? So basically, we need to find a transformation that maps 4 vertices in here to 4 vertices of this rectangle. Makes sense? And of course, for such region, it's very easy to integrate because, you know, whatever you write, dx dy or dy dx, x and y in this case, you know, basically are not depending on each other. So you just write integral from where? From -4 to 0, that is about the y, right? And the x is about 1 to 4. That's it. So it's very easy to work with such, you know, region. Makes sense? I want to mention one more thing. When we study Riemann sums, right? And when we determine the double integrals, we always use squares because of this reason. Makes sense? All right, so let's do that. I need to find a transformation, okay? So suppose that we have u equal to x plus y and u equal to x minus 2y. Look at this, y. Where is x plus y? X plus y is right here, right? This term. And when you change, so x plus y equal to 1, that means this straight line. You see? This straight line. And when x plus y equal to 4, so you have this straight line. Make sense? So basically, if you put u equal to x plus y, you map the line x plus y equal to 1 to the line u equal to 1, and x plus y equal to 4 to the line u equal to 4. Make sense? Similarly, you can put v equal to x minus 2y, because, you know, when x minus 2y is 0, that is, you know, the u axis in here. Makes sense? And when x minus 2y equal to -4, so you get this straight line. That's it. That's why you put, you know, u equal to x plus y and v equal to x minus 2y. Okay? So from here, you need to solve for x and y, because you need to find the functions x and y depending on u and v. U and v in this case are new variables. Okay, so let's solve this for x and y. From here, I can get x equal to 1/3 2u plus v, and y equal to 1/3 u minus v. It's pretty easy to solve, you know, such system. Like if you want to find y, you subtract the first, right, and the second. So x will be cancelled out. So you have 3y equal to u plus minus y. That's why you have the second one. And then you plug it back to the first one, you get x. Makes sense? All right. Now, you write the following map. Your map look like this. T, u and v equal to x and y, right? Because x and y is a function, and you want to use, you know, the map T to consider to transform your original region in rectangular region. And of course, that is 1/3 2u plus v and 1/3 u minus v. If you write this map in the form of matrix, you will have the following one. That is equal to 1/3, 2/3, right? In here, 1/3. In here, 1/3 and -1/3 times u v. Look at this. It's pretty easy to understand. So for example, whether you take 2/3 in here. That is the coefficient of u, right? Where's 1/3 in here? That is the coefficient of the v in the first coordinate. And then 1/3 and -1/3 are from here. Make sense? And you apply to u and v. So when you multiply, you know, this matrix 2 by 2 with this vector 2 by 1, you take the first column and multiply and consider the dot product of the first column with this of the first row with this column. Make sense? So you have what you need. This is the linear transformation we need. Okay, now I want to find Jacobian of this changing, because we already changed from x to y to u and v, right? Let's find Jacobian. J. So I need to find determinant, right, of the following matrix. I need to take partial derivative of x with respect to the u. That is 2/3. You see? And partial derivative of x with respect to the v. That is 1/3. Similarly, I have partial derivative of x with respect to the u is 1/3, and of y, and then of y with respect to the v is -1/3. So basically that is equal to -2/3 times 1/3 minus 1/3 times 1/3, and this is equal to -1/3. Okay, now let's apply this to the following integral. We have double integral over s of 3xy dA. Okay, and we already know the Jacobian of the linear transformation from s to r. So I can apply that right here. I will rewrite this as r, okay, 3x. What is x? We have x and y right there. X is 1/3 2u plus v, right, times y. Y is 1/3 u minus v. All right, and here I will have Jacobian. I need to copy this Jacobian right here, multiply with -1/3. Okay, and du dv. Of course, I need to work, you know, with the integration limit in here, but that is pretty easy. We already saw that in the region R, u goes from 1 to 4, and v go from -4 to 0. Makes sense? So I have the following one. This is from u is from 1 to 4, and v is from -4 to 0. All right, and now we just evaluate this integral. So let's simplify a little bit. Here I have -1/3, 1/3. This will be cancelled out, so basically I will have -1/9. Okay. I think we need to take the absolute value of this, of the Jacobian. But that's fine. That is, you know, the difference only in the size, so we can live with that. So I think I mix absolute value in here. Here we should have absolute of -1/3. So we have 1/9 integral from -4 to 0, from 1 to 4, and then 2u plus v times u minus v du dv. Okay, let's open parentheses, and then we can separate, you know, this double integral, and we can rewrite it in terms of product of two integrals. So I have -4 0, 1 4. I have 2u squared minus uv minus v squared du dv. Okay, so that is 1/4 -4 0, 1 4 2u squared du dv minus -1/4 0, 1/4 uv du dv and minus negative 140 v square du dv. I write in this form because I want to separate, I want to rewrite as product of single integrals. Look at this. For this integral, we have 2u squared without v. So this is equal to integral from 1 to 4, 2u squared du times negative 4 to 0 dv. Right? And here we have uv. We can separate that, negative 4 to 0. v dv times 1/4 u du and minus negative 4, 0. Here I have v square dv times 1/4 du. Okay, so now we just need to evaluate each integral, but I think that is pretty easy. So let's say the first one, we have 2 over 3 u cubed evaluated from 1 to 4. This is equal to just 4 because 0 minus negative 4 is 4, right? In here I have 1/2 v squared evaluated from negative 4 to 0. In here I have u squared over 2 from 1 to 4. In here I have v cubed over 3 from negative 4 to 0, and here I have just 4 minus 1. So if we simplify everything, we should get the following answer. Here should be 164 over 9. Okay, and of course that is what? That is the volume of our solid region, right, over this region. Makes sense? So I think I finished my lecture right here, and I also finished the course. If you have any questions about this and about the material of Calculus 3, please feel free to let me know. All right? Thank you.